Good morning, class. Today we are going to see the numerical based on the last equation that we have derived or we came to know. That was Rydberg equation, or we can call Rydberg formula. So the formula is, this is wave number equals to R, and in bracket 1 by n1 square minus 1 by n2 square. Or it can be wave number equals to 1 by lambda equals to the value for R, we can take it as 109678 per centimeter, or in meter it is 10.9678 in 10 power 6 per meter. Okay, and 1 by n1 square minus 1 by n2 square, where n1 and n2 are integers. That may assume the values from 1 to infinity, with the requirement that n2 is always greater than n1. Okay, that you have to keep in mind. Now we'll use this equation to solve the numerical based on the spectral line series of hydrogen. Okay. So the question is calculate the wavelength of the third line in the bracket series for hydrogen. Okay, so this is the question, and the value for R is given 10.97 into 10 power 6 per meter. Now, how to solve this numerical? So as we know from the Rydberg equation is 1 by lambda. This is the value for R, 10.97 in 10 power 6 per meter, and 1 by n12 minus 1 by n1 square minus 1 by n2 square. Now, from the bracket series, if you table the last table that we discussed, table 2.2, there all the details of the spectral line is given: first line, second line, third line. Okay, now according to this statement, the value for n1 will be 4. n1 will be 4, and the value for n2 will be 7. The reason is that for the third line, since the first one is Lyman, Balmer, Gaussian, then bracket, this is the fourth series, we can say. So in the fourth series, the value for n1 is 4. The value for n1 is 4, whereas the value for n2 will be, for first line it will be 5, for second line it will be 6, and for third line it will be 7. So the value for n2 will be 7. Now we have got the value for n1 and n2 from that table 2.2 for the third line in the bracket series. Substituting this value of n1 and n2 in the above equation, okay, we get like this. So we'll simplify it, 1 by 4 square and 1 by 7 square. Then after that, when you just simplify it, it will come as, this whole value will reduce to 0.0420918, and when you multiply this with this one, it will come as 461747 per meter. Okay, now, or you can also since this is 1 by lambda is this much, so when you take the reciprocal, that becomes only lambda, what will happen? 1 will be divided by this value, so which will come as 2.1 into 10 power minus 6 meter. So this is how we can solve the numerical based on the Rydberg equation. So based on the same type of numerical, we have got the assignment for today. Calculate the wavelength of the spectral line when the electron in a hydrogen atom undergoes a transition from an energy level with n equals to 4 to an energy level with n equals to 2. Okay, so over here you have to calculate the wavelength where n, the higher value is n equals to 4 and the lower energy level is n equals to 2. That means we need to use which series? First one is Lyman for n equals to 1, lowest value, and for second one n equals to is for Balmer. So you need to use the Balmer series over here. The value for R is given. Similarly, question number 2, calculate the wavelength of the first line for the Lyman series of hydrogen. Lyman's first line, where the value of n1 is 1 and the value for n2 is 2. Okay, first line of Lyman series, and the value for R is given in centimeter. And question number 3, calculate the wave number. And this one you just calculate not energy, wavelength. Okay, wavelength G dh, wavelength. So calculate the wave number and wavelength associated with the second line in the Paschen series for hydrogen. Once again, you have to use in a similar way. You can refer to the table 2.2 for the value for the second line, which will come what will the value for N1 and what will the value for N2, and the value for R is given over here. So you'll find it, the wave number and wavelength.